Hi, everybody. Here I am with the solution to section 2.2, exercise 16 by request. So let V and W be vector spaces that have the same dimension, and let T be a linear transformation between them. Show that there exist ordered bases beta and gamma for vector spaces V and W respectively, so that the matrix that represents the linear transformation with respect to those two bases, that is this T bracket sub beta super gamma, is a diagonal matrix. So we've got these two vector spaces that have the same dimension. We've got some arbitrary linear transformation. We don't necessarily know anything about it other than it is a linear transformation. And with only that information, we're going to be able to choose two bases, choose a basis beta for V and choose a basis gamma for W that forces this matrix to be diagonal. So here's how we're going to start. Consider the null space of T, which is a subspace of the vector space V. We can choose a basis for the null space of T. Some subspace, so it has a basis as well. So I'll call it U1 through UK be a basis for the null space of T. So note then in particular what this means is that we're calling the dimension of this K, the nullity of T, if you'd like. Okay, well, that's not a basis for V certainly, but we can extend it to a basis by the extend to a basis theorem. We can extend this to a basis. I'll call it beta prime for the moment. Let's see why shortly. I'll call the first vectors U1 through UK. And then the remaining vectors, just to distinguish them, I'll call them V's, but I'll continue numbering them VK plus 1 up through V sub n. And so note here that I am implicitly calling the dimension of V n, and by hypothesis, that's the same as the dimension of W. Great. So now we have a basis for V, but the first K of the vectors are very well controlled when we apply the linear transformation T. T sends each of those vectors to 0, because that's what it means to be a vector in the null space. The remaining vectors then presumably don't go to 0, or else they would have been part of a basis for the null space. In fact, they're going to be a basis for the range. To see that, let's sort of recall how the dimension theorem was proven. Well, what we did was we started with exactly the setup. We began with a basis for the null space. We extended it to a basis for V, and then we tried to apply the linear transformation T to each of the vectors. So then T of beta prime is equal to just the set T of U1 up through T of UK, and then T of V K plus 1 up through T of Vn. But remember, each of the U's was in the null space, so this is really just the 0 vector in W, K times, and then T of the remaining vectors, T of VK1, K plus 1, up through T of Vn. But we still know that the range of T is equal to the span of T of beta prime. But since T of beta prime consists of a bunch of zeros, together with the remaining vectors, this is exactly the same as the span of the set T of Vk plus 1 up through T of Vn, since zero vectors do not increase the span of the set. All right, so that's great. Now we've got a generating set for the range of T, but in fact, we can say more than this. Not only are these vectors T of Vk plus 1, T of Vk plus 2, up through T of Vn, a generating set for the range of T, but just as in the proof of the dimension theorem, these form a basis for the range of T, right? In general, when you start with a basis for the vector space V, and then you apply T to each of the vectors, you don't necessarily expect to get a set that's linearly independent. In fact, we can see that over here. T of beta prime was certainly not linearly independent because it had a bunch of zero vectors in it. However, this set, T of Vk plus 1 up through T of Vn, that is a linearly independent set. And one way to see that is to observe that by the dimension theorem, so either you can use the argument in the proof of the dimension theorem, or since we know the dimension theorem, we can use the theorem itself now. By the dimension theorem, the dimension of V, which we called N, well, that's equal to the nullity K plus, well, it's the dimension of the range. So in other words, the dimension of the range is equal to N minus K, which is the size of the set, T of Vk plus 1 up through T of Vn spans R of T and has the dimension of the range of T vectors. So if you have the right number of vectors in your set, namely the size of the dimension of the vector space, then being a spanning set also implies that you are linearly independent. So this set is also linearly independent. So if it spans the space and it's linearly independent, then it forms a basis. Not for all of W, mind you, but a basis for the range of T, which is a subspace of W. Okay, so if we want a basis for W now, we can extend this to a basis by the extend to a basis theorem. We can extend this to a basis for W. Let's call this gamma. This will be T of vk plus 1 up through t of vn. And then I guess we need k more vectors of w1 through wk. All right, so now we've got a basis for v. We called it beta prime. And we've got a basis. Actually, let's add a prime here just in case we need to adjust things here as well. So gamma prime is this t of vk plus 1 through t of vn, and then extended to some other vectors in w, w1 through wk, and that's now a basis for w. So let's consider now, what does the matrix with respect, the matrix for t with respect to these two bases look like? Well, what we're going to want to do is apply t to each of the basis vectors in beta prime. So beta prime was up here. It's u1 through uk, and then vk plus 1 up through vn. So we'll do t of u1, t of u2, up through t of uk, and then t of vk plus 1, t of vk plus 2, up through t of vn. So these are going to be how we figure out the columns of the matrix. What we need to do is to write these vectors in terms of the basis for w, this gamma prime. So in other words, I want to write t of u1 as a linear combination of these vectors right here. Well, t of u1 is just the 0 vector in w, so I guess I could write that as a linear combination with a bunch of zeros. That's equal to 0 times t of vk plus 1 up through 0 times wk, which means that the first column of this matrix is going to be consisting of all of these coefficients. It's going to be all zeros. And that's fine for a diagonal matrix, because all we need to do is make sure that we have all zeros off of the diagonal. So the top left entry will be a 0, and then all the rest will also be 0. So that's fine. And we're going to see that exact same behavior for all of these vectors in the null space. When we apply t, we just get the 0 vector. So we're going to be able to write this as a linear combination using only zeros as coefficients. That's true all the way up through t of u sub k. Zero times w. Okay. All right. But now, when we get to this next bit, t of vk plus 1, and we want to write it as a linear combination of these vectors from gamma prime. Oh, t of vk plus 1 is one of the vectors in gamma prime. So I guess when we go to write that as a linear combination, we're going to try to write it as 1 times t of vk plus 1, and then 0 times everything else. T of v sub k plus 2 up through, well, all of the other vectors, all the way down to wk. Similarly, t of vk plus 2, that's already one of the vectors in this basis gamma prime. So we're going to get 0 times t of vk plus 1 plus 1 times t of v sub k plus 2, and then zeros for the rest. T of v sub k plus 3 all the way down to 0 times w sub k. And finally, this t of v sub n, well, that will also be one of the vectors from gamma prime. So we'll get mostly zeros as coefficients until we get a single 1 as a coefficient times t of vn, and then zeros for the rest of the vectors. Okay, well, that seems fine, except that this t of vk plus 1, written as a linear combination, these are supposed to give us the, well, the k plus first column of our matrix, and we have a 1 first and then a bunch of zeros, so that's not right for writing down a diagonal matrix. So we're going to have to fix some stuff. Really, the problem was the order. When we wrote down our beta prime, we started with the basis for the null space, u1 through uk, and then we extended to the v sub k plus 1 up through the vn. But if we start with the v sub k plus 1 up through vn as the first n minus k vectors in our ordered basis, then use the t of v sub k plus 1 up through t of v sub n as the first n minus k vectors in our second ordered basis, then we'll be in a position to write these as the first n minus k columns of our matrix. That will be perfectly diagonal, and then the remaining columns will be all zeros, which will still be diagonal. So let's fix that now. Let beta be the vectors v sub k plus 1, v sub k plus 2, up through vn, then u1 up through uk. So remember, there are n minus k of these and k of these, giving us n vectors in total. And let gamma, well, we were actually okay when we named gamma prime in the first place, so gamma is gamma prime. It's the set of vectors t of v sub k plus 1, t of v sub k plus 2, up through t of v sub n. Again, there are n minus k of these, and then these other vectors that don't actually matter that much, it turns out, w1 through wk that we got when we extended to a full basis for w. Then when we go to write down the matrix for t with respect to this basis beta and this basis gamma, well, we're going to observe that t applied to the first basis element vk plus 1 is going to be t of vk plus 1, which is 1 times this guy and then 0 times the rest. So we're going to have the column 1, 0, 0, 0 all the way down. Then when we go to apply second vector in this basis, we're going to be able to write it as the first element of gamma plus 1 times the second vector of gamma plus 0 times the rest. So the column 0 and then 1 and then a bunch of zeros. And this pattern will then continue, allowing us to write each of the first n minus k vectors after the transformation as 1 times the corresponding vector in gamma, going on diagonal for the first n minus k columns. And then after that, once we start applying t to the remaining vectors, t of u1, that will be the n minus k plus first column. Well, t of u1 is just 0, so all of the coefficients, when we write them as write 0 as a linear combination of gamma, all the coefficients will be 0. So is including on the diagonal, and that will be true for all of the remaining vectors in beta. So all of the remaining columns will be 0. Leaving us with a diagonal matrix. Hopefully that was clear. Hopefully the discussion of the beta prime and then correcting it to the beta was clear and helped by way of motivating where the solution might have come from. Please feel free to ask any follow-up questions, or we can discuss it in class. And I will see you guys on Tuesday.